Okay. So in last lecture, we have studied instruction that was MVI. What does that instruction do? That will do immediate data transfer from the immediate address to your register. Okay. So who is going to provide the immediate data? That's the question. So immediate data would be provided by user itself. Like if I am going to write a code, then I am going to provide this immediate data. Though I am not going to provide this immediate data by any other means. I mean, like I am not going to enter it data through keypad, but rather than that, when I am programming at that time, this data is important, and that's why I am saving this data prior to some register. Okay, so this is how immediate data transfer operates. The data from the next address would be copied to the register specified using this R. The registers can be A, B, C, D, E, H, L. Okay, so in general term, we can say this is an immediate data transfer operation where the immediate data will be moving to register R. What are the operations involved while executing this instruction? There are two operations involved. First one is opcode fetch, and the second one is memory read. Opcode fetch will fetch the opcode of MVIR. Once it fetch the opcode is, let us say, 06. So once it reads 06, it knows that immediate data transfer has to be done, and 8085 automatically go to the next address and bring the immediate data and move it to register R. So that's how this operation works. Now this whole explanation is given in the book in detail. Somehow Addr is not working. Just a moment. Yeah, okay. This is the book of your microprocessor architecture programming and application with 8085. It's like a huge book on 8085. We are not interested in the whole book, but what we are interested in is some architecture and some programming. That's the part that we are going to use. So mainly we'll be having chapter 1, microprocessor, microcomputers and assembly language, introduction to 8085 assembly, microprocessor architecture and computer system, architecture and memory interfacing, and then this bus. Up to 4th chapter we are going to cover, and from that also we'll be skipping so many parts. Now let's begin. Now let's see in the book what is given in the book. See, this is a general purpose microprocessor system. Like this whole block of data is given just to explain this thing. What is microprocessor, what is memory, what is input and what is output, and why we need it. We have already done this. Okay, so this is just explanation of like what is memory, why we need memory, what is input, why we need input, why we need output, how the input, output, and memory can communicate with each other or with your processor or controller. So that's all thing is given. Then this block diagram is internal of your CPU, you can say, or traditional block diagram of a computer. Okay, so in this we know that part of CPU is ALU. So CPU is basically central link processing unit, and inside your central link processing like central processing unit, there will be two part, one being the arithmetic logical unit and the other one is the control block. So this is again a general purpose computing system, how it works. You can read this things easily. You do not have to mug up even these things. Okay, just you can like the question can be asked on this system, so you just need to have like a general block diagram you must know. Okay. Otherwise, in details like this cannot be asked. This is not at all related directly. We'll learn this later on. Okay, and then this is the evolution of processors. See, Intel microprocessor historical perspective. So since 1971, they have started to build up the processor. The first processor that they have built was 4004. This is the name of processor. The number of transistors involved inside this processor was 2300. So using 2300 transistors, they have built up this processor, and this clock speed or frequency of operating frequency of this processor was 108 kilohertz, address bus of 10 bit and data bus of 4 bit. So basically you can say this is a 4-bit processor, and it can only have a 640 byte of memory. Okay, this is very less. Then they have evolved over years, and 85 was invented in 1976, which comprised of 6500 transistors. 5 megahertz is the speed. So I have told you roughly 1 to 3.6, but it is actually 5 megahertz, and like it depends on variant to variant, it may change. 16 bit of address bus, 8 bit of data bus, and 64 kilobyte of memory that we can address. We have done this, how to calculate the 64 bit. And then they have going on, and then they have Pentium in 1993. Okay, now you see this number is going increasing exponentially. It was doubled somewhere here, it was like 5 times somewhere here, then 4 times, then again doubled, and then they started in millions. Okay, so this is 1.2 into 10 to 6, so it is 12 lakh. This is 30 lakh, 50 lakh, and then they have crossed the crore. In Pentium 4, you will have 42 into 10 to 6 transistors. It can operate at 1.4 gigahertz. It has 36 bit of address bus, 64 bit of data bus, and so this is, you can say, a 64 bit architecture. And then 64 gigabyte of memory is possible using this controller. So this is how your controller processor has evolved. Like processors of Intel has evolved. This is basically related to Intel only. Yeah? There are other competitor of Intel who were producing, like Motorola was one of them. Then Dallas Semiconductor is one more company who is competitors of this microchips or processors or controllers. Then organization of a microprocessor based system, we know that how things work. So this is a general purpose diagram of 8085, you can say, or any other microprocessor based system. Okay, you will have ALU, you will have control block, you have register array. So we have seen ALU in 8085, we have seen register array, register A, B, C, D, E, H and L is the register array. We have seen the control block. There is a system bus. System bus is address bus as well as your data bus and control bus. Combining all three is a system bus. You can have input output with them and ROM. So this part, this inner part is actually your processor, and then you are going to connect something outside. That is your input output and your memory. And this is again a little bit of explanation of that things. Then this is interesting. How does a microprocessor work? Okay, this is generalized. Like this, everything written in this book for first chapter is generalized. It is not related to 8085. Then what is machine language? What is the language of 8085? So I have told you the 8085 understands actually binary, and we write in terms of hexa, but actually it will be binary language. And we understand assembly. So what is binary language and what is assembly? Like what is machine language and what is assembly language? The difference is given over here. You can read this on your own. ASCII, we are not interested. Writing and executing assembly, not interested. High level language, not interested. Operating system, not interested. From large computer to single chip microcontrollers, not interested. This is not important. We have this kind of hardware. Okay, this is the single board microcomputer, the printer. This is the printer, old printer, some old printer is there. We will have this kind of hardware of 8085. I will show you in next class. So these parts are not for use. But we'll start from chapter 2. This chapter 2 and beyond will be helpful to us in actual course of 8085. Okay. So see, this is a general purpose programming model. Like this is a 8085 programming model. Why programming model is given? Like you do not have to mug up this diagram. This is a programming model. The diagram that you are going to mug up is different. I have shown you earlier. And we have discussed there are various registers in 8085. So these registers are given just to explain the programming of 8085. Once you learn everything, you'll understand this. What is this thing? Okay. There are some registers, definition of register, which are the registers, definition of accumulator, definition of flag register. I have not covered this yet. I'll come back to this later on. Then instruction classification. Okay. So mainly 8085 can have this kind of operations. That means data execution. First is data transfer operation. We learned data transfer operation. We know two data transfer operation, and that two data transfer operation are MOV and MVI. That two are data transfer operation. So what is a data transfer operation? Data would be transferred from one register to another register, or one place to other place, or memory to register, or register to memory. That's a data transfer operation. Okay. If you just moving a number from one place to another place, that's a data transfer operation. Then there can be arithmetic operation. Which kind of arithmetic operation? It can have addition, subtraction, increment, decrement. We'll see example of all of these operations. Okay. Then it can perform a logical operation like AND, OR, rotate, XOR, compare, and complement. Then it can perform branching operation. Why branching operation is needed, we'll cover it later, but the branching is jump and call. Now here onwards, see from here onwards they have started with instruction set. Okay, so mainly your 8085 will have three kind of instruction size. 1 byte, 2 byte, 3 byte. We have seen 1 byte instruction, we have 2 byte instruction. We'll see 3 byte instruction in near term future. This is the again example given of 1 byte instruction. Then there would be 2 byte and then 3 byte instruction. So see, this is how books goes. Like it does not explain what is MVA, but it's directly started on the size of instruction. That's why I do not say okay, follow the book. This is the reason. Okay, then opcode format. Now 2.32 is not of use at all level. Okay, this is how opcode has been made. Like I told you, okay, opcode for move AB is 78 or MVIB is 06. So how that 06 come in the picture? That story is hidden inside this theory opcode format. But we'll be not going in this. Data format will be not going in this as well. How to write SML and execute a simple program. This is the good thing, but we are not going to follow this. I'll have my own method that you can follow. Okay, so this is chapter 3, all about chapter 3. These are all the instructions. See, from this point, these are all the instructions that you can have on your 8085. 8085 cannot perform operation other than listed over here. For an example, અહીંયા કોઈ instruction એવી નથી કે જે multiplication કરી શકે. That means you cannot perform multiplication in 8085. This is all the operations that can be performed over 8085, and all the assembly instruction are given for that operation. This is operation and this is the menomics. What is a menomics? That is a general purpose how we write that thing. For an example, move RD, RS is a menomic of moving the data from one register to another register. This is example and this is operation. Okay, so if I want to ask in exam, I'll follow this menomics. So this is operations that can be performed using 8085. Writing and handling assembly program, not interested. The theory I am looking for is not here. Yeah, from this point onward you have to read this 3.1.1 microprocessor initiated operation in 80. I'm going to take this books, okay, and I'll let you know what is the part of book that you should follow and you should not follow. So see, this is the block diagram of bus structure. We have studied what is address bus, we have studied what is data bus, and we have studied what is control bus. So 8085 will be connected with address, data and control bus. and on that 3 buses, various devices would be connected. For an example, a memory, an input and output. Now there can be have more than 2 or 3 inputs, more than 2 memories, and more than 3-4 outputs is possible. But all the devices would be connected with same bus. See, this is a single address bus. All the devices would be connected on this same address bus, and all the devices will have its own address. Like for an example, this memory. This memory can have a range of addresses starting from 000 up to some number. Okay, we'll see that while we study memory interface. Okay, this is the diagram which I was looking for. See, this is the theory. Where is starting point? Starting point. Yeah, this is the starting point. First read this theory, internal data operation and 8085 register. This is very essential theory to understand how data moves inside and outside 8085. So yesterday, let me just copy this figure, and then we are going to have this example. I hope this figure is visible to everyone.
Yes, sir.
Okay. Now there are some basic features to this figure that I'll explain. This one. This is the address bus. This is my address bus. Okay. This is my data bus. This is 8085. This is a memory chip. Sorry. This is a memory chip, and there is a control signal. Okay. See, the name is memory read signal. Now I have stored my program. I have stored my program inside my memory. This is my program. See how a program looks like. This is actual program. This is actual program in machine language. Okay. Now to convert this program in machine language, you first need this hex numbers. These are the opcodes. Like what you see on left side are opcodes, and each opcode have its own instruction. જે અહીંયા નથી લખેલી બરોબર છે, but દરેકની એક instruction છે. Now see, inside a memory you will see only these numbers. Whenever there is a memory, you will see this kind of thing only inside a memory. Okay, and along with that, અહીંયા તમને જે આપેલું ચાલે these things 2000, 2001, 2002. These are the addresses of the memory. These are the address of memory. Like Jim, you have a society, and inside a society you have house number. Same way, this is a memory chip, and inside a memory chip there are n number of locations. So n number of locations must be uniquely addressed. So these are the addresses. So I can say on address 2000, 06 is stored. On 2001, 78 is stored. Same way 2002 is 3, and 2003 is F2. Now how the internal thing works, like how a program executions take place inside 8085. So first of all, to understand that, I must explain what is PC, or known as a program counter. What is a program counter? A program counter is a 16-bit register which will look after execution of sequence of your program. So basically this is the register which will handle after which line of code, what would be the next line of code has to be executed. That is taken care by program counter. So initially, when you reset the 8085, the default content of program counter, no register is blank ever. So default content of program counter is 0000H. Okay. Why you see 4-digit number? Because it is a 16-bit register, so it can have 16-bit of data. So hexadecimal number 0000 is a 16-bit data. Okay. So on reset, when I heard reset 8085, ये तो मैं power switch off करो mobile. Same way when you reset 8085, at that time the default content of your program counter will become 0000H. Now what I will do, when I start to execute the program, at that time first I'll let 8085 know where my program is written. The first thing that I'll do when I start to execute the program is, where is my program? I'll tell 8085 where is my program. And how to tell him? By giving him this number inside a program counter. So what I'll do, when I want to start execution, at that time I'll replace this number with the number from where my program is stored. So in our case here, my program is stored at 2000H. First line of my program is stored at 2000H. First line. नीचे JK बीच है, but first line is stored on 2000H. So who program counter, like, so I'll copy this 2000 in program counter. How to do that? I'm not interested, but I'll do this is for sure. Okay. So my program counter will start with 2000. So immediately, what it will do? Once I let him know that my program is starting from 2000, what 8085 will do? 8085 will go to 2000. Now, what is on 2000? My first line of code. So I am sure that my first line of code is on 2000. That means this is not a number, but this is opcode for me. First line of code is opcode, is always opcode. It cannot be a data because I'm storing a program. So program my first opcode is and followed by opcode, it can be a data. So first on 2000 it knows it is a opcode. So what it will do? It will put this 2000 on this address bus. So 8085 put 2000 over here. Okay. So 2000 is everywhere now. Everywhere our address bus is 2000. Now program counter has 2000. That means there is a first line of code. That means code must be read. Code has to be read from memory. I am not writing code. I am reading code. I want to execute the code. What I'm going to do, I'm going to read that code. But it is a code. That's why we call it something different. But this is basically opcode. So I'm going to read opcode. So what I have to do? I know the address. I have put the address on address bus. The second thing that I'll do is I'll send a signal to memory that I want to read the status of given address. So what I'll do, I'll send a read signal from this line. First task was to put an address on address bus. Second task, send a read signal. As soon as I send the read signal, immediately this 06 will be available on my data bus. Now this 06 that is available on data bus will come inside of 8085 and it will directly go to which register? Instruction decode register. Now instruction decoder registers knows what does 06 mean. Okay. So what does 06 mean? So it knows 06 is opcode for MVI. As soon as it comes to know this, that 06 is the code for MVI, it will again ask what is the data now. Okay, what it will ask? What is the data? So immediately 8085 will go to immediate location. That means now it will take away this 2000 and it will take the new address, that is immediate address, that is 2001 on my address bus. Now along with that it will send a read signal to memory that I want to read data on 2001. 2001 is given by address bus and read signal is given by control bus. As soon as it do this, this 06 will be moved from data bus and new data will come here, and that is 78. Now the 78 will come inside. There is an internal data bus on 8085. It will come on to internal data bus, and the instruction decoder has already given the signal that immediate data has to be moved to register B, because 06 means MVI B and immediate data is 78. So now once 78 comes inside, it will be automatically transferred to register B. Okay, it will automatically transfer to register B. Why? Because first instruction was given was 06. The 06 means transfer immediate data. So it will automatically get the immediate data and move it to register B. Okay, this, other than the fetching the opcode, all the process will be done by itself. There would be no human interference in between. Okay, you just have to give 06 and 78. Once this task is complete, what will happen? Now instruction decoder know that MVI was 2-byte instruction. So my next code would be on whatever was the content of program counter plus 2 is the next address of instruction. So it knows the next instruction is 2002. So automatically the content of program counter will be updated and it would be shifted to 2002. Who will do this? This will be done using instruction decoder and your timing and control unit. The two part will combinedly change this content of program counter, and the program counter will directly become 2002. So earlier it was 2000, now it has become 2002. Say 2001 nathi thayun. Why? Because 2001 was data. How I know that? Once I get this first opcode, then and then I come to know that this is the data, and then I realize that 3 is the next opcode. So again, it will, what it will do, program counter will put 2003 over here. It will bring 3 inside, and then it will try to understand what does 3E mean. So 3E is the code for MVI-A. 3 is the code for MVI-A. So what it will do, it will again put 2004, try to bring in data, that is F2. So F2 will come inside and F2 will be moved to A2. Now what would be the content of program counter? Again, the instruction was MVI, it's a 2-byte instruction. So again, it would be program counter plus 2. So 2002 plus 2, it is 4. So 2004 is the next destination for code. So my next line of code is 80 over here. What does 80 mean? 80 is add B. So once 80 come inside, it knows now it is a instruction to add 2 numbers. So it will automatically add 2 numbers and store the answer in accumulator, and then whatever is the next step would be followed. This is how a program executes inside your memory, microprocessor. Okay, and this whole explanation is given in this block. You can read it. So if you do not understand it, you just read this 2 pages, 61 and 62 of book. You will understand everything. Okay. Now, what's the next topic on the book? Next topic is memory. We have learned this DQ flip-flop. Then I have also shown you this figure. There are 2 tri-state buffer over here. One is for read signal, one is for write signal, and then combining them like this would create a memory. So this is a memory. Okay, there is a 224 decoder. To decode the address bus would be connected to decoder, the input buffers would be there, then output buffers would be there, and there is a stack of registers. This is how a memory is created. Okay, this is the explanation of memory. We have already done this, and then this is the advanced memory that we are going to use. Okay, so just for information, read this, just for information. Okay, then this memory we are going to cover, and we'll learn that in details, but just read these things, like how memory is created. We have covered in first lecture. Don't read these things. Memory map and memory addresses will come to this later on. And there, yeah, this is a topic for the self study. Write down topic for self studies 3.2.7 memory classification. This is just the classification of memory, like what kind of memory is available: static memory, dynamic memory, EEPROM, EEPROM, what are all those things. Okay, don't mug up this one diagram, but what you are actually going to do is read these things. What is static RAM? What is dynamic memory? What is ROM? What is EEPROM? What is mask ROM, pre-ROM, EPROM, EEROM? Just read this. What is flash memory? Okay, just read that things. Input output will skip all this part and will directly go to chapter number 4. And chapter number 4 is actual starting of 8085, where you will have this is a pin diagram of 8085. We'll cover this later on. And then there is a block diagram. This is the block diagram that we are going to write whenever asked. Architect of 8085, then you have to draw this block diagram. This is internal data bus and ALU instructional decoder, all the register. We have already seen this figure, so you must be having this figure. We'll cover this figure at the end, then you will understand this figure in better way. Okay, so now the main parts are covered. Now let's move to this diagram. This is very good diagram. The diagram of this figure is known as timing diagram of instruction, or timing diagram of any instruction is this. Whatever I explained you over here, like how it is done actually, is explained by this diagram. If you have any instruction inside your 8085, then this is the timing diagram of how things are done. Okay, once again I'm going to give all the details about this diagram. I'm not drawing this diagram because it would be very difficult to draw this diagram on this thing. That's why I'm just explaining this diagram. Otherwise I would have drawn this, but it is not possible to draw this using this writing pen. So let us start how to draw any timing diagram. Suppose you have been asked in the exam, draw the timing diagram for this instruction. Okay, what would be the question? Draw timing diagram for instruction MVI A32H written on address 2000H. This would be the question. Instruction and address would be given. Might be opcode will be given. Let us say opcode for MVI A is given, and that is 3EH. Okay. So what is the information that you have? You have first information, what is the address? So write down the address. Now this instruction is written on this address. What does that mean? The opcode of this instruction would be stored on 2000H. Okay, so opcode is 3EH. So it would be like this. Then you know that MVI A, 32 is 2-byte instruction. That means it would be having 2 byte of data. This is only single byte data. See, this is only single byte data. You will have 2 byte of data. So obviously next byte of data would be stored in next location. What is that data now? This data would be immediate data itself. So here MVI A, 32. So 32 is my data that would be stored in next location. This is the basic information that you need before drawing this diagram. Now how to draw this diagram? So first of all, start with clock, draw the clock. Now how to decide how many number of clock I have to draw? So to decide that, you need second set of instruction, second set of information. First information થઈ ગઈ, address and data. Second set of instructions are what are the operation performed to execute this instruction. We always know first operation is opcode fetch cycle and second is memory read cycle. We have learned this yesterday, how why it is memory read. Okay, 32 is data, so memory read would be performed. So first is opcode fetch and second is memory read. We know that it is 4 and this is a 3 state instruction. So 4 plus 3, total 7 steps would be there in this diagram. Okay, first cycle would be opcode fetch. See, this is opcode fetch. So draw it like this. First I'll have starting from T state T1, T2, T3, T4, T5, okay, up to T4, and then again T1, T2, T3. If you don't follow this, you can write T5, T6, T7 as well, no issue. First thing is this, take 7 equal parts. Then I'll first draw the clock signal. Okay, see now how to draw a clock signal. It should be actually like this. It should be actually like square wave. But when you zoom in with CR on any clock signal, it is not at all a square wave, but rather it's a trapezoidal wave. So start with maximum point here, go down in somewhat like tilted line, 0 for some time, again coming back high with a little bit of tilted line, and then 1. Okay. So at this point I am completing my 1 cycle. Now next cycle I will start with going down. Okay, so this is the point where I am completing my first cycle. Draw such 7 clocks because I know there will be 70 states, so I have to have 7 clocks. So these are the 7 clocks that I am first drawing. Now whatever below that has to be drawn by you, and that is nothing but 8085 do. So we know that 8085 will have program counter will have 2000. So first thing that program counter will do will, now program counter at 2000, it will give this to address bus. So first is the data on address bus. What would be the data? Address. What is the address given by program counter? In our case, what would be that? It is 2000. So first of all, address bus would be given 2000. Now see how address bus is drawn. Here I have drawn AD0 to AD7 and A8 to A15. So AD0 to AD7 is my address plus data bus. It is my address plus data bus. No separate data bus is given for 8085. Address and data bus are multiplex. That means that two are working as a one. Address આવશે તો બી એક જ same place and data આવશે તો બી same place. Okay, like single road છે, એ single road થી અમદાવાદ બી જવાય અને બરોડા બી જવાય. Now you decide where you want to go, but road is single. Okay, but the traveler knows the journey, એ ક્યાં જવાનું છે. Same way here address and data bus is multiplex. So first step છે address. So initially address would be available on address bus. So address bus પર આવ્યું એ ટાઈમિંગ ડાયાગ્રામમાં બતાવવાનું છે. Okay, actually I am drawing this diagram to understand when and where things will be available. So first address bus ઉપર data would be available. So see how to draw this. I'll make this transition. Okay, whatever earlier I don't know. So this is a transition from something to new thing. So I'll put this. What would be here? Here it would be 20. Why 20? So higher order address bus set. So A15 is this side and A0 is this side. So A15 to A8 would be 20 and A7 to A0 would be 0, 0. So 20 on A8 to A15 and 0, 0 on AD0 to AD7. Okay, so combinedly this two makes address, that is 2000. Now along with that address 8085. Now as we seen here, address and data is multiplied. Now how to know which one is the address and which one is data? So 8085 send a signal along with this, and that signal is known as ALE. This signal ALE would be sent only if AD0, AD7 has address on them. 8085 internally knows which is address and which is data. So what it will do, whenever it will place an address on AD0 to AD7, it will send this ALE signal. So ALE signal will notify okay, AD0, AD7 has address and not data. So ALE would be helpful to understand whether the address bus has a data or address. So if ALE is high, that means this is address. If ALE is low, that means it is a data. Okay, so this is the first step. Now along with this two, it sends a memory read signal. It sends a memory read signal. How to send a memory read signal we'll see later on, but this is how to send it. IOM bar is equal to 0, S1 equal to 1 and S0 is equal to 1. So combinedly this 3 is my opcode fetch signal, and along with that there is signal RD bar that is right now not sent. See, it is high but it is not sent. Okay. So it will send this 3 bits of data which will specify right now opcode fetch cycle is going on my 8085. Now once this stage is complete, I will move to next stage. Now on next stage, no change of data on higher order address bus, but on lower order address bus, I will remove the addresses from the lower order address bus. Okay. So lower order address bus is free now. Then no ALE. Why? Because no address is on AD0 to AD7, so no ALE will be sent. Opcode fetch cycle is still going on, so I'll not going to modify this status until 4 T states. And then your 8085. Now see, address is available on address bus. Now what I will do, I'll send a read signal. How to send a read signal? By having a low. So after your second P state start, after some time, I'll send a low signal. Now as soon as I send a low signal, the buffer of my memory will open up and it will send the data from inside. Like here data that has been sent to out. As soon as I send this read signal, same way, this is actual read signal RD bar. As soon as I send it, immediately my memory will send the data from internal. What is the data right now? It is 3E. So 3E would be sent it to data bus, and that 3E would be available up to 1 cycle. But when it is available half of T2 state, so it will be available up to half of T3 state. So it will be almost available for 1 T state starting from half of T2. See, data is available after T2 is completed, like half T2 is completed, and then it is available up to half T3. Okay, so until and unless my read signal is low, up to that time my data would be available on data bus. Where this data came from? This came from memory. And once that completed, my T3 cycle is also going on side by side. Still the higher order address bus at 2000, data bus still have 3. Opcode fetch cycle is still going on, read signal was still low. At the end of the T3, it has been sent again high. So what will happen? As soon as I put this high, my data would be vanished from data bus, and I'll have a one more T4 cycle. During this T4 time, my instruction decoder will work and evaluate the instruction. What is the instruction? And it will do the needful. During that time, my address bus would have a state which is unspecified, or you can even draw a dash like this instead of unspecified. Data bus unspecified, AL is still low, no changes. Opcode fetch is still going on, so no changes on this cycle, RD bulb will be still high. When T4 completes here, now it knows like what is the instruction. Instruction is 3. I have to move the data, immediate data to register, some register. So it will get the immediate data. Where is immediate data? Address is 2001. So again this cycle will start. Again address bus will have 2001. So 20 on lower higher order address bus, 01 on lower order address bus. But as soon as it puts a address on lower order address bus AD0 to 87, it will again send an ALE signal. And along with that it will send the status of the cycle going on, and this is memory read cycle. So this 010 is for memory read. We'll see that at some point of time, but right now I am just letting you know this is a memory read cycle. It will send a memory read cycle, and RD bill is still high. Then after some time, when it has given enough time for the address to move, it will send a read signal by sending RD bar low. As soon as it do this, again a memory will give me data, that is 32. Okay, at somewhere around mid of T2 state, and that data will be available up to T3. And once this complete, during this time my data will be moved to register A, and the cycle will end over here. So this is how you draw a timing diagram. Okay, now the hidden secret is the timing diagram will always look like this. The only thing that will change, if you did not understand why when things what things come here, just mug up this thing. What are the changes? I'll let you know. What are the changes, or what might be added, or what might be removed. If there is a opcode fetch cycle, draw this diagram up to this part. Okay. If there is a memory read cycle, draw this yellow part. That would be always same. What would be the data that is changing? The data that change would be this number, this number, this number. Same way here, this number, and this number. This is the only data that changes. In examination, this diagram can be asked, so you must know how to draw this. But the hidden secret is that this is the only data that always changes on timing diagram. Okay. What is timing diagram? Timing diagram gives the internal information when and where various things would be high or low. Okay. So using timing diagram, you can know when the data is available, when the address is available, when ALE signal will go high, when the status signal is so and so, when the read signal will be sent. You can know this all things using timing diagram. Okay. And this is how it is drawn. Now if something has changed, like for an example, તમને address અલગ આપ્યું છે. For an example, તમને address કીધું છે, let me change the color of the pen. Like તમને જે address કીધું છે, that is this 3000H is the address. Let us say 3000 બી નહીં, એવું કીધું છે 3000. Let us say 3010 is the address. And તમારો opcode છે 60. હું randomly કહું છું, મને ખબર નથી what is 60, but આવું કીધું છે. So what would be changed? So you know this is, if this is only 1 byte instruction, there would be only opcode, and in that case you are not going to draw this part. You draw this part. What would be the change? Change would be here. First address bus આવશે 30, lower address bus પર આવશે 10, and મારો opcode આવશે 60. Done. Now this is the correct diagram for this second instruction. Same way memory read cycle માં કઈ change થાય. For an example, if the immediate instruction is there 30, 11, 20, so you'll write 30 over here, 11 over here, and 20 over here. That's all. Okay. So this is how you draw a timing diagram, and this is how things works inside your 8085. Done. If you have any question, you can ask, or we'll move forward with instructions, new instructions. If you have any question, you can ask.
No, sir.
No,
Clear.
sir, clear.
Okay. Then we'll move forward to the next set of instructions. Let us start to have to learn a new instruction. And rather than like directly learning a new instruction, what we are going to do is we'll have a program, and with the program I'll explain you the new instruction. Let us say this is a program WALP. What does this mean? Whenever I write this, that means write an assembly level program. Assembly level program. A stands for assembly level program. Okay. So WALP to add number 20 and 30 h. But this is the question. Let us say this is the question. Write an logical program to add number 20 and 30 h. Okay. Now see, first of all, how to write this program. So first of all, the number given to you 20 and 30 are actual data. You do not have any keyboard to enter that data. So what you have to do is you have to somehow move this number inside your 8085. We know that how to move the some numbers inside 8085. Can anyone help me with this? If I want to take this 20 inside 8085, which is the best instruction that you know? Before you process data, data must be stored. That's the hint. Before you process the data, data must be stored. So 20 and 30 are data, so it must be stored somewhere inside 8085 from where I can access it. Okay. So what I'm going to do, I'm going to move these two numbers, one in accumulator and other one in register B. How to do this? Let me know. Let me ask someone. Roll number 20, Jay. I want to transfer number 20 in register A. What is the instruction? Number 20 in register A. What is the instruction? Jay. Jay, please unmute yourself and answer me. If you are not there, I'll mark an absent for today's lecture. Then Tejas will give the answer. Tejas, roll number 26. I want to move number 20 in register A. What is the instruction? Tejas, I'm not able to
Yes,
hear
sir.
you.
Yes,
No.
no.
Sorry? I am not able to hear you.
No idea, sir.
No idea. We only know two instructions as of now in 8085. One is MOV A, B. Here a register data transfer occurs. This is immediate data. This is actual data. So this instruction won't help. The only other instruction that you know is MVI A, 20 or R, 20 or R, data. So we know that here this data is specified. This is also data. That means you can use this instruction. Now the other question, what can be R? R can be A, B, C, D, E, H, L. Here A and B is given. That means I can use this instruction. So first instruction would be MVI A, 20H. Second would be MVI B, 30H. Now two data is available inside my 8085. One data is in register A, the other in register B. Now question is how to add this two. You don't know that how to do that. So to add two numbers, or rather to add two register is possible using 8085 by using add instruction. Instruction is ADD add. Okay. How it is written? Add R. What is R? R can be your register A, B, C, D, E, H and L. So if I want to add register A and register B, what I should do? I should write add A and add B. Then the question is, where is the answer now? So to learn that, you must know what add instruction will do. So basically this add instruction will add two registers. Okay, two registers is for sure, but which are the two registers? Which are the two registers? So first register is always register A or accumulator, and second register is register R specified by you, this R. Okay, so if I write add A, what will happen? It will add accumulator with accumulator itself. If I write add B, what will happen? It will add accumulator with register B. If I write add C, what will happen? It will add A plus C. So now you understand why accumulator was there. A register A was there near your ALU. See, accumulator is here and ALU is here. So all the arithmetic and logical operations is being performed on register A, accumulator. That's why it was near there. So whenever you perform any addition, subtraction or logical operation, if there are two registers involved, one register would be accumulator itself. Always. कोई तमने के ना के. Accumulator is always there. Second register, if a second register is there should be specified, like it should be specified by a user by writing this. Okay. Now apna case ma, in our case, what we need to add two numbers stored in register A and B as of now. So A and B add karwa hoy, then what I can do? I can write add B. So thase automatically register A plus B થઈ જશે. Now next question, where is the answer? So once you execute this add instruction, the answer always stored in A. So whatever is the answer always will be stored in register A. So once you do this, the answer 20 plus 30, that answer 50 would be always stored in register A. That means the register A content will change from 20 and it will become 20 plus 30, that is 50. So this is how a program is done. So this is the program of adding two numbers using 8085. Okay. If you have any question, you can ask. Any questions? If you don't have any question, I have a question. We'll start with rule number 13. Rule number 13, unmute yourself.
Yes, sir.
Yes,
Yes,
I have
sir.
a question for you. What is the size of this instruction? Add. Like MOV is 1 byte instruction, MVI is 2 byte instruction. What would be the add? Like add kitla byte ni instruction hase? Guess करवाना चाहिए.
Sir, 3 byte.
Why 3 byte? See, away like a secret bhi gaye, like how to identify what would be the size of instruction. Please unmute yourself. Sorry, please mute yourself.
Okay,
So
sir.
how to identify any instruction, the size of any instruction? See, if you see this kind of instruction, let me have an example. If you see the instruction, for an example, this instruction. Okay, then you can have this kind of instruction. So just look for the data available along with the instruction. Okay. If there is no data available with the instruction, that means it's always 1 byte. If 1 byte of data, 1 byte of additional data is available, it is 1 plus 1, 2 byte. So which is the 1 byte initial 1 byte is of opcode. The additional 8-bit data is opcode plus additional 8-bit data, 1 plus 1, 2 byte. And if you see in 16-bit data along with the instruction, then in that case it would be a 3-byte instruction. What are the 3 byte? 1 byte for the opcode. So opcode is always there for each instruction, and 2 byte for my data. Which data? 16-bit data. Here it is 2000. So this is the key, how to identify the size of instruction. Okay, next question to roll number 11. The area.
Yes, sir.
What would be the operation, like opcode fetch, memory read, memory write, input read, input write, output write? What would be the operations performed while executing this add B instruction?
Input read.
Input read. Okay. See, now one more thing. Whenever there is an instruction have opcode, and opcode is always be fetched. That's the first point. So whenever anyone asks you a question like what would be the first cycle, always say opcode fetch. You will be always correct. Because 8085 must understand first what it has to be done. Who is going to tell him what has to be done? Opcode is the way. So first, always opcode will be fetched. By understanding the opcode, 8085 will know what is the next step. But in first step, always it will fetch the opcode. Now, a second secret. If your instruction is 1 byte having only opcode, there would be most of the time, like 99% of time, there would be only single operation, and that is opcode fetch only. If you have only 1 byte instruction like this, there would be only one cycle, and that is opcode fetch itself. No other cycle would be related. If it is 2 byte, there would be opcode fetch plus one more cycle, and if it is 3 byte, so opcode fetch plus 2 more cycle. But here the game might change, like sometime it may have 2 or 3 more cycles. But for single byte data is opcode itself, and opcode has to be fetched. So always a single byte instruction will have opcode fetch cycle only. That is the second secret. Okay, keep these two things in mind. Yes. Okay, now any question? No question is very good. Like you are excellent student. I'm happy. Any doubts? No doubts. Okay, there is a comment here. Network issue. Jai Shara.